My name is Nicola, and you're watching Singularity FM, the place where we interview the future. If you guys enjoy this podcast, you can help me make it better in two ways. Number one is you can go to iTunes and write a brief review, or number two is you can simply go to interviewthefuture.com and become a patron. Today, one of the rare occasions when I would actually have two guests on my podcast, Danko Nikolic and John Smart. Danko is a cognitive neuroscientist and an AI expert who headed a research lab at the Max Planck Institute for Brain Research. Currently, he is the head of data science and AI at EvoCenta, a co-author of the Handbook on Data Science and AI, and the originator of the Practopoiesis theory of intelligence, which we discussed in a fantastic interview a few years ago. And I very strongly suggest that you guys go and check it out because I believe it is more relevant now than ever. John Smart has taught and written for over 20 years on topics like foresight and futurism, as well as the drivers, opportunities, and problems of exponential processes throughout human history. He is president of the Acceleration Studies Foundation, co founder of the Evo Devo research community, and CEO of Foresight University. Most recently, John is the author of Introduction to Foresight, and we also did a fantastic interview on that with John that I strongly suggest you guys go and check it out. Also, his book, of course, which is literally the handbook for futurism. Presently, John is co writing on the thesis that both deep neuromimicry and deep biomimicry will be required to create increasingly smart, wise, and safe AI systems. Now, the reason that I have brought both John and Danko here today, besides the fact that John Smart, being very smart, came up originally with the idea, so we have to give him credit for that, is to discuss the future of AI in general and specifically their respective theories of practopoiesis, neuromimicry, autopoiesis, biomimicry, and the AI alignment problem. Our plan here today is to have John walk us through autopoiesis, perhaps for the first 20 or 30 minutes, then have Danko follow up with his theory on practopoiesis, and then we would finish with a 1 hour discussion on the AI alignment problem and many other relevant AI topics. So, welcome to Singularity FM, guys. I'm so excited to have you both here today.
It's an honor and a true pleasure. Thank you so much.
Yeah, it's an honor also from my side.
Well, fantastic. So let us just dive right in here and begin our conversation with perhaps John Smart's taking over the podium and giving us a big, a short introduction about autopoiesis.
All right. Well, autopoiesis is a term that was used in the 70s and 80s by systems theorists. I was trained as a systems theorist under James Miller. He wrote the Living Systems Theory tome, where he compared physical and informational processes from individual cells all the way to the entire ecosystem. And he was looking for commonalities and differences. That's what systems theorists do. And this term gained some traction because people realize as we struggle for definitions of life, there's two really obvious things that are incredibly important to life. Well, three really, but the two basic ones are that it replicates, it continually copies itself, and it continually varies. So it copies and varies. And you can talk about evolutionary processes as a process of creating variation under selection. And you can talk about developmental processes as a process of conserving the critical structures of any replicating system in a chaotic and contingent world. And so auto, self, and and replication, and poiesis, creativity. I'm mangling the Greek roots here, but those two concepts are evolution and development, kind of continually working with each other. And if you think about evolutionary processes, they're going to very easily break developmental processes. Evolution is crazy and chaotic and experimental and exploratory. And development's the opposite. Development's conservative and cyclical and predictable. Evolutionary processes very quickly become future unpredictable. Developmental processes are future predictable, but only within the life cycle of the system. If you've seen a previous cycle, like an acorn turning into an acorn tree, creating more acorn seeds, you can make these statistical predictions about it. And if you have a developmental model, you can do the same. So those two concepts kind of work together to create life. And in the 1990s, a theoretical branch of biology called Evo-Devo emerged as a way to improve our understanding of evolutionary theory. And there's a few thousand publishing theorists in this space. It's a pretty small space. But one of the great things that has emerged from Evo-Devo biology, as it's called, is an understanding that there are the fundamental set of regulatory genes, the control parameters of the replicating system, that are highly conserved in evolutionary history. And they, most importantly, they constrain evolutionary processes. The way that they are located in the genome, they constrain what can be created. So an Evo-Devo perspective on a replicating system requires us to balance the constraining processes that unfold the complex adaptive system and the exploratory processes that create new systems and then feed in some of those parameters to the fundamental control parameters. And one of the really interesting insights of evolutionary developmental biology is it's really only a very small subset of control parameters that are involved in development. About half of our genes are regulated in development, but only 10% of our genes are highly regulated in the process of developmental expression, and only roughly 5% of our genes are highly conserved across evolutionary species. So you've got I call that the 95-5 rule. About 5% of these control parameters are so critical that you can't mess with them without breaking development itself. And the other 95%, you see them changing across evolutionary history and between different families. You see a lot of variation. And somehow that variation is fed back into the developmental control parameters in the next cycle, but in an accretive process. The accretive meaning it building on top of the original developmental code. And so my thesis, if you will, is that this autopoietic system, there's one last thing I need to say. The thing that is the critical survivor in an Evo-Devo system is not the individual, which is the experimenter evolutionarily, right? It's not the group, which is the thing that is protected on a normal distribution in developmentally speaking. It's the network. It's the network of individuals and groups. Life as a network, particularly at the genetic level, has just continually increased its evolutionary and developmental complexity under all the previous catastrophes, which have sorted out, the KT meteorite or Cretaceous Paleogene extinction got rid of 75% of the species. But how much of the actual when the asteroid hit, but how much of the actual genetic complexity disappeared? My argument would be virtually none. Virtually none. At the critical network levels, these catastrophes, they're almost like selection events that actually increase the complexity of the control parameters. So my argument would be that these evolutionary and developmental processes in an autopoietic, self-maintaining, self-creating system. That's the definition I should have started with, right? A self-maintaining, self-creating system. They're probably going to be critical in the future of these AI systems, because right now they're facilitated autopoiesis. You can think of them like viruses, which require cells to replicate. All the existing AI systems, we're using our intelligence, our rationally guided models, which we think are primarily top down, but my argument is no, they're actually rationally guided guesses. Not 5% top down. We have these theories, but 95% of AI design, in my argument, is this evolutionary stochastic experiment guided by these control parameters, which we call rationality, right? And so my argument is that's a weak and limited system. What's going to happen when we start to figure out not just neuromimicry, which we're doing now, and Danko is going to tell us tremendous insights on how to do that better, but biomimicry, where we have a gene equivalent, an analog to a gene, hardware description language in our AI systems that unfolds not only a neural network, not only does it specify an artificial neural network, it specifies an embodied network with its sensors and its effectors. So it's an embodied intelligence, just like we are. And then that system is selected either in a simulation environment very quickly by various parameters, or in a physical environment where it's tested like an embodied robot that has to, pick up and wash dishes or whatever it is. And so this field that I just described, evolutionary computation or evolutionary algorithms is the classical approach to this, but it's missing what's called artificial development, the ability to actually have this hardware description language and these gene analogs that specify these two types, these genes that conserve and these, or parameters, if you will, that conserve, and these parameters that create. And so that would be my definition of what deep biomimicry would be. And I would love to hear Danko's and your and everyone else's thoughts on, is this really the future? Are we not only going to create AIs that mimic more of our emotions and our ethics and our neural processes, but that actually are more like living systems like us, but in this new substrate? And if so, does that tell us that there's this major convergence ahead for biological and technological or cybernetic intelligence? And what does that future of AI look like, and how do we make it wiser and safer? And so that's my opener, and I think I'd love to hear Danko's and your thoughts.
Thank you very much, John. That was an absolutely fascinating introduction to autopoiesis. And it has, I think everyone can clearly see, it has major ramifications, major implications to the way we perceive intelligence in general, to the way we perceive life in general, even. And of course, to the way we are trying to recreate our intelligence and our life on another substrate, non-biological substrate. So the next guest here, Danko Nikolic, has a very unique and original hypothesis about how exactly we can accomplish that. It deals with the origins of intelligence, it tells us about how it works, and it tells us a lot of good lessons about what we can take from his Practopoiesis theory and apply those lessons into the designing or the creation of artificial intelligence. So, without further ado, Danko Nikolic, you have the virtual podium, my friend.
Hi. Yeah, thank you. So, hi everybody. Thanks for the invitation. Great pleasure, great honor to be here. Nicola, we did already once some years ago. It was great pleasure back then, and I'm so excited to repeat it. And John, really thank you for the introduction, because it's a really great basis for what I would like to describe. And so I have to first make a point that I started my thinking, my work, my career from a different perspective. At the beginning, I wasn't interested in life. I wasn't interested so much in evolution. I was interested in the problems of AI. AI had problems, still had problems, didn't reach the levels that we hoped for. So I was like spent time working. Time means years, not short time, working on how to figure that out. And over time, I get to realize that AI you cannot solve with algorithms and equations. That you have to see how the brain works, how the biological intelligence works. So I actually derived my career. I went into cognitive science, into neuroscience. I learned how to do brain surgeries, study the brain, get dive into it, trying to figure out the secrets out of the brain. And I had some ideas, and I want to explain now how I got these ideas, what is the idea, and how this led me back to biology and to life, and how this all connects with Evodevo, how I think it connects with Evodevo. So to like you, John, described like there are two basic components: evolution, development. You have like two big boxes, two things that are important and playing a role in this development. Now, the brain science and AI in the same time had also two boxes, two different boxes. One box was the network that computes. Like you have a network with synapses, connections, all of that computes, you put input, produces output. If the network is well connected, everything's done right, it's going to be an intelligent network. It's going to do some smart stuff. That's one box. The second box was the learning of this network. So how do you get the network to be smart is that you have another box. It's the learning, is the what we call in neuroscience plasticity, but it's the same thing biologically, your development. It's the same thing. It's expression of genes that build the network in the brain. And in AI, it's simplified, it's something else, but the purpose is the same. Build a network. So I have two boxes in AI and in the brain science, right? And one of the boxes overlaps with your boxes. Okay. Now, here's my insight. They took a long time to get to that. And the insight is that for the brain science, we don't have two boxes, but we have three boxes. We have three boxes. So the two boxes that we discussed, the plasticity and the connections, we have to pull them apart, and in between, the biology has built a third box that was hiding from us in plain sight. All the information was there, the data were there, anatomical data, physiological data, behavioral data, and we were ignoring it because it was just too complex for us perhaps to understand it, or we could go pieces by piece and explain everything with two boxes. So we just kept ignoring it. It was just too much for it. But that's basically the fundamental idea that the mind, the intelligence, that all the powers of human intelligence are in this third box that's sitting in the sandwich, and that we were missing about. And what theory of Practopoiesis was about was understanding the relationships between these boxes. You can also call it components, or how I called it in the theory, different adaptive levels. Right? So in your Evo-Devo, the two boxes, you have one adaptive level is evolution, changing the genes. And a completely different adaptive level is development, interacting with the environment to build the organism autopoietically. Right? Now, here we have, like for learning, the same development, interacting with the environment to develop the neural network. You also had a neural network interacting with the environment, creating behavior, all the necessary stuff that organism needs to survive. And then the idea is now we have a third box in between these two that's actually results. What we see as a result of these boxes is our thoughts, our cognition, our experiences, everything's in this third box, right? So what's interesting is that if that's correct, then intelligence cannot be like really in the connections and the synapses, but there has to be some other physiological aspect. And just recently, I think I figured out which parts of the physiology should be responsible for this third box, and these are metabotropic receptors and G protein gated ion channels.
Just a short plug in here for everyone. I should have started in my introduction that Danko recently published an absolutely mind blowing, fantastic science paper called Where is the Mind Within the Brain? Transient Selection of Subnetworks by Metabotropic Receptors and G protein gated ion channels. I highly suggest you guys Google this paper. It's about 12, 13 pages. It's not very long, but it's profound. It has profound implications about how intelligence works, and how we can potentially recreate it, and even where consciousness may reside. It's absolutely fundamental, so I highly recommend it. And I know he's very modest, so he may not plug it. So I'm going to make sure I plug it in for him here. Sorry for the interruption,
Okay.
my friend.
Thanks, Nicola. So so got this, like, hopefully nailed down the physiological aspect, right? But what is really interesting probably for us here is the whole relationship between life. So and one fundamental question is, like, if we count now how many boxes we have. I mentioned we have evolution, we have development or learning. This is number 2. Number 3 is this new one with these metabotropic receptors and the other tongue twister named proteins. And the 4th one is the network that results. So we have in total 4 adaptive levels that interact with each other. And that's for what I concluded at the end, that must be the life. These 4 levels is how you define the life, right? And that's how I developed the Practopoiesis theory. I try to understand generally how they interact, how they work together, so the whole thing doesn't fall apart. And what are the advantages if you add another adaptive level, another box, or if you remove one? What are the costs? How difficult it is to add one, and so on. So that's what the Practopoiesis theory is about. Right? Now, why I named it out Practopoiesis is exactly because it's a continuation of the theory of Autopoiesis. And Autopoiesis tells us that the organism develops itself, and Practopoiesis tells us, basically breaks this down. It's like which pieces of the organism build whom. It's not that always that this molecule builds this one and this one. It's not just reciprocal always. There's some hierarchy inside, and this hierarchy I kind of broke down into 4 different boxes at the end. Right? And maybe as the last thought, what I would like to say, why poiesis? Why the word poiesis? It's really beautiful, and we should contrast it to what we usually do in AI. It's computation. So we consider AI as a computational problem. A computation means you put numbers in, crunch, 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 numbers out. Now, when we say computation, what we think is that you have some numbers, some results out, where usually certain intelligent being has to come to it and interpret and use those, right? You have some information, and when you have information, somebody has to know how to interpret this information. Now, the concept of poiesis says, no, you don't produce really information. You could, but it's not emphasis. The emphasis is that you produce some product, some artifact that has a life on its own, even though it's not really information. You don't really consider it as information. Like if you produce this pencil, that's an artifact. If you produce this cup, that's an artifact. So does a learning mechanism produces an artifact, a neural network that can do stuff. The result of learning is not information that somebody would like consider it as decoding information. It's just a result is a machine that does something useful. And so is result of development is a machine, a body that can do something. So is the result of evolution that produces at the end new type of genome that can produce something new, and so on. So it's always at this hierarchy of these boxes, these adaptive levels, they poetically affect each other. And how this all works is through actions. You have to always interact with the environment in order to keep this whole thing intelligent. So that's where we have to change our focus if we want to understand intelligence and if we want to create more artificial intelligent machines. We have to think in terms of poiesis rather than in terms of computation. Although they're similar, you compute stuff at the computer at the end, but still changing the way how you think is very helpful. So maybe I stop here and then we see what Nicola has as ideas. How do we continue?
Thank you very much, Danko. That was, and John, by the way, anything with poiesis inside of it, whether autopoiesis or practopoiesis, is highly poetic and beautiful to me. I hope our audience can appreciate it too. I think the original idea of autopoiesis is very powerful, very strong. I don't know if I should use the word classic, but it's just seminal. And then I think Danko's idea of practopoiesis, original as it may be, is even pushing it a little further. It's even breaking it down a little better. It's explaining it a little better. It's making it come together a little better. It's just like, that's why I like it so much. And that's why I think it all makes sense. So I think we can all see that those two theories are actually not mutually exclusive, but actually mutually supportive. They work together in sync, I think. The question is, what do they tell us, right? What's the implication here? So let's start first on the negative part, and then we'll move to the positive part. Even though John here has given me very strong instructions that I should start with the positive and then move to the negative if I want to be a better, more productive futurist.
Yes, sir.
So let's start just with a slightly negative implication and potential for it. So maybe it's even non-existent. Do autopoiesis and practopoiesis tell us that we cannot create AI, that we cannot create artificial intelligences?
Okay, I guess I would say the exact opposite. I think autopoiesis, if you take it broadly, it tells us that intelligence is trained in any replicator that is able to stay stable. This starts with the simplest autocatalytic sets that Stuart Kaufman talks about in his At Home in the Universe and his other books about this idea that we need a fourth law of thermodynamics to explain the emergence of life. We need something to understand self-organization. Well, self-organization, from an Evo-Devo perspective, is something that's stably replicating and stably creative. It has to be creative to create that variety so that when something crazy happens, most of it gets selected out, but the ones that don't, suddenly they have all these new resources and they do more creativity, and you see this beautiful evolutionary fan out. So it feels to me that if we're going to run into complexity limits with design of facilitated autopoiesis and facilitated practopoiesis, my take on practopoiesis is Danko is giving us hierarchies that are important within these networks and relations between those hierarchies that we're not getting out of standard autopoietic theory. So he is pushing it to that next level to help us see what's missing in current AI design from the network perspective and how we get to the next level. My argument would be we need that plus some fundamental expression language that's similar to genes that allows the AIs themselves to start taking over these evolutionary or creative and these developmental or conservative features. So I would say if you look broadly at AI or look broadly at life from that perspective, I would argue you're going to hit a complexity threshold with facilitated autopoiesis. You won't with these natural methods. And so I think to get to what we call general AI, we're starting to see that there's going to be real limits on what we can do, even with all the amazing advances, which we haven't talked to. I'm gonna wave a few books and things on these new advances in AI, but still, I think they pale in comparison to the complexity of living systems.
Being a good futurist, John preempted. foresaw and preempted the direction that I was trying to take our conversation into. So, which I shouldn't be surprised about. So Danko, uh, is that what's been the missing piece? Is that, in other way, the reason why, despite the fact that Marvin Minsky thought in 1956 that computer vision would be a summer school project for his TAs and stuff like that, 60 years later we're still struggling with not only computer vision but any you know uh, progress with respect to artificial general intelligence? Is Practopoiesis the missing piece? And does it tell us that if we actually start embedding that kind of design or structuring or layering of the system as you propose, we have the best perhaps chance to get that missing piece right and to create finally artificial intelligence?
Yes, this is exactly my opinion. Uh, and that's why I built a theory, right? So I think that's what we are missing. We have to think differently, we have to organize ourselves differently in order to feed machines with intelligence. So basically, what we have been doing so far we, was not good enough in a sense that we did not have insight into the difficulties of the whole problem. So, in a way, what the Practopoiesis is telling us is that it's more difficult than we thought, and it's pointing us where it is difficult and which challenges we have to attack. And I think John is exactly precisely saying it. It's the genome or the machine genome or the equivalent of a genome. If we had this solved, everything else would be easy. Then we could just treat the machine as a baby and nourish it, feed it, play with this, and it would just grow and become intelligent. So the hardest part is to get this genome right. For us, of course, it took some hundreds of millions of years of iteration to get it right, or the best we have so far. Now we wanna do it in a shorter period of time, but we cannot do it if we don't understand the whole problem. Where is it problem? Where is the role? Why is it so difficult? Where are the limitations? We have to start from there in order to start building this genome and start finding shortcuts. I think we can find a lots of shortcuts. We don't have to repeat the evolution. And the reason why we can do the shortcuts is that we already have one solution that was created by evolution. So we can copy and paste many things from there. Not everything, but we can copy and paste a lot and then make up for the rest through maybe something like evolution or something like. So we can shorten the process quite a bit.
Let me push back here a little bit, Danko, because uh, correct me if I'm wrong, but the reality is, I think nowadays you two guys are probably the minority. And the dominant paradigm, if I may call it this way, is kind of the deep learning algorithms. So much so that, recently I had here Joshua Bach, who is a fantastic cognitive scientist in his own right. And I asked him the same exact question. And here's what he told me. I gave him the sort of classic Noam Chomsky criticism that tells us that programs are, in a way, like an insight about how the mind works or how intelligence works or should work. And they, in theory, should give us new insight about how that process of intelligence works. And unless and until we lack that, we're not making any progress. In other words, Noam was putting the good old idea about that we need a theory of mind in order to create AI. Joshua told me he used to think that himself. However, he said that after working in the field of deep learning in the last few years, he actually changed his mind. And now he thinks that that theory of mind is going to kind of emerge or come out of the models that they're working with, one way or another. So he thinks, in other words, that it's not like you start with the theory first and then you create models that reflect the theory and therefore you make progress. You obviously, you either kind of deny the theory, falsify the theory, or you support it and therefore make progress. He actually thinks that you create the models first, obviously, as they've been doing in many ways, and then somehow, don't ask me how, there would be an emergence of that new theory based on the new insights that develop while using those models. That's his idea. And, again, correct me if I'm wrong, but I think that this is the dominant opinion right now in the field of AI, especially in the context of some honestly mind blowing successes that we have all witnessed in the past decade using those algorithms by companies such as DeepMind. And most recently, the example that Joshua was giving was DALI 2, as one kind of pretty cool and impressive example of what AI can do right now. It's like the current cutting edge. And how very quickly that developed from DALI version 1, which was only just a couple of years ago. And all of this is based on not having a theory of mind, not using what Practopoiesis tells us to do, and just kind of going in a completely different way. So if we are here at a kind of a global conference, you guys would kind of be almost sitting on your own. Is that true?
Well, why don't I jump in first? The model I'm pitching is you need deep neuromimicry and deep biomimicry. And I think we're being forced. I think AI designers since 2011 have been forced into deep neuromimicry because of the success of the deep learners. And I would argue that they were forced further into neuromimicry with the emergence of these reinforcement learning systems, which model how dopamine works in the human brain. There's a fantastic Nature paper, which I mentioned in my Substack, that describes how dopamine works. Only 1% of our neurons, but each dopaminergic neuron is connected to over 1 million other neurons. So it's this very special, among the 50 neurotransmitters we use, it's this very special reward neurotransmitter that we use. And they had to copy that in something called temporal difference, or TD learning, to create these really significant breakthroughs at DeepMind that we saw with AlphaGo and these other not only deep learners but reinforcement learners that are rewarding themselves. And I would argue that the emergence of transformers, which is now the new hot topic, that's attention. That is an attempt, a crude attempt, to copy how attention works, to guide the deep learner, which now has a crude model of emotions, it has a crude neural network, and it has a crude model of attention. And that's transformers. I'm going to wave this economist as a futurist. You always want to pick one magazine. What's one magazine you're going to read weekly? I would argue this is the one, right? Because economists, they have a beautiful, once a year they look ahead for one whole year. It's called what the world in, and then they give you the next year, and they have a what if section that goes through, like, what if Finland tried to sell part of its country to Russia, for X dollars. Like, so it's a beautiful, and they just did this AI's New Frontier, which has DALL-E on the cover. Right, this is a DALL-E created image that they fed in this AI's New Frontier, and this is what they got. So what's my wrap up here? My wrap up is, these are called foundation models. A foundation model that employs all these features, these basic deep learning, this reinforcement, and this attention, this transformer capability, training on now up to 1 trillion parameters in the top models, right? They have this foundational ability. So let's say you train them on a language model, they can actually work for image recognition. Not well, but they work. Previously, they never worked. So there's this general flexibility, if you will, to these particular models. Now, I don't know how well that fits with Joshka's concept of theory versus model, but and this might be a great question for Danko to tease out. But I would argue that they're being forced into more and more specific neuromimicry, and I'm just saying biomimicry is going to be the next thing. At a certain point, they're going to stall out in what they can do. The complexity is going to overwhelm them. An AI designer working with a trillion parameter model has no freaking idea what to do next. They need to read papers by the great cyberneticists, by Danko, and these other people that are focusing on that today and really saying, no, these are the relationships that are critical. And those are what are going to guide them, I think, out of the morass toward these fundamental parameters where the machines can start doing it themselves. So that's my take on your fascinating question.
What about you, Danko?
Yeah, thanks, John, for that. Like a good background as the question. So, I mean, this game of you have two towers. You have a creative, productive people without fear and just go and build machines. It's like, we are doing it. We are going to build it. Look how great it works. And then you have on the other side, kind of people who are thinking, looking from the side, and saying, I'm not sure this is good enough. Right? And when you look at the history of AI, this was just always like that. And both had good points and wrong points. Both had good predictions and wrong predictions. But the fact is that people were saying the same thing 50 years ago. We are doing it. We have it. We solved it. And the other guys were said, I don't know. You didn't figure this out. You are still missing this big thing and so on. Now, this same story is repeating. The same story is repeating. Now, I was trying to, I'm maybe more on this, partly I'm on this other side saying, this is not yet there. But still, I'm trying to offer a solution. I'm not just complaining. Right? I'm trying to offer a solution. Like, why don't we do this instead? Now, I was trying also to find some argument of where it's wrong today that would not be easy to dismiss, right? Because in the past, everything was easy to dismiss. It's just philosophical argument. You were like, Searle would say, your models do not understand. And then they spend, 20 years discussing what does understanding mean. Nobody agreed ever. That was just not a strong argument, like the Chinese room argument, thought experiment. I don't need to probably re-describe it here. But it didn't really, just pissed off everybody. Everybody hated everyone else. Right? So I thought, can you quantify this problem? Right? And I think we can quantify it today. And there have been a few papers in the literature who were studying the intelligence of the problem, if you can put it on the x-axis, and the size of the resources you need to solve the problem. Right? And John, you mentioned trillions of parameters, and the developers of these models, they very proudly say, like, we have trillion parameters, and the other guy says, we have 1.5 trillion. Then the next one says, like, we have 2 trillion. Then China comes, we want to have the biggest one with 5 trillion, and so on, as if this is good. And it basically, what I'm saying, this is all bad. This is, the more parameters you have, this is worse. It's just, you should be kind of ashamed of having so many parameters, not proud. Why? Because this curves, like intelligence versus the number of parameters, what these curves empirically look like. When we look at all the models around the world, they're all power law curves. It means that they just explode. The amount of resources you need explode. And this is true for the number of parameters, but also from the sizes of the training data sets you need, and from the number of computations and iterations and repetitions that you need to actually get to them. So reinforcement learning, same curve. Language, same curve. Vision, computer vision, same curve. So what does that mean? We can extrapolate the curves. And when we extrapolate the curves, the numbers look really, really, really ugly. If you estimate the amount of intelligence, the variety of different situations a human mind can resolve, And you can estimate, it's really hard to say, like all the possible things that the human mind could solve, all the process, like an adult human, let's say 30 years old with average knowledge, how many different situations a human could, act reasonably good and kind of if the
Near
and
infinite, I
solve a
would
situation.
suggest.
Near infinite, yes, but numbers are really huge, many, many, many zeros. If you make this estimate, right, you could do some tricks and make these estimates, but you get many zeros, 40 zeros, 60 zeros. It's like flirting with infinity. Yeah. Now you look how much intelligence models today have, how many different things they can resolve. These are much, much, much smaller numbers. So you could do extrapolation and look like how many resources would I need given the power law curves to get to roughly to human intelligence with today's technology. And I did this estimate, and it turned out you would need like a computer of the size of Milky Way galaxy. You would need, the training time would be much longer than the age of the universe, and things like this is what the numbers you get. Of course, you estimate. So it's, in one estimation you get size of the galaxy. Then this is optimistic, little less pessimistic, you get size of the universe very quickly. Right? So so it doesn't really matter exact numbers that you get, but what matters is the nature of the curve. The curve is a power law with an exponent larger than one, and it means it goes up, right? And some people estimated this exponent. And one study in a computer vision, by looking at all of the numbers, estimated that this exponent is about 9. It means this is horrible, horrible, horrible. 9. And 2 to the power of 9 is 512. It means that to double the intelligence, you need 500 times more resources, 500 times more parameters, 500 times roughly bigger data set, 500 times more computational power. And that's why these models are so huge today, and only some big organizations can afford them. That's why GPT-3, the huge language models and the follow-ups, I cannot get one at home. Neither anyone, neither even big companies cannot get one, can afford one. Only the biggest companies and governments. Right now, recently, German government has jumped in to get a German GPT-3. No company in Germany could do it without the help of the government. Right? That's sad. That's shaming. Right? And yet, you take human on the street of Germany, and they do better job than this huge machine, right? In terms of language, so they understand better language. They create new languages. You give them some unusual object, they describe it in a language. You ask them weird language questions, they do much better than the computer. Right? So that's the problem. That's the quantified problem.
Can I jump in as a futurist? I'd like to paint a few scenarios for you to consider, Danko. And Nicola, jump in on any of these too. So like one, so many people did not expect these parameter scalings to work. There's a quote in the Economist article, Oren Etzioni of I forget, Allen AI Institute, saying, everybody thought as you scaled to hundreds of millions of parameters, you would just eventually hit an S curve and you wouldn't get benefit. But as far as they're going, they're still getting additional improvements. Now, they're not as big as they used to be, but they're still getting improvements. But the weird thing is they're also getting more flexibility now with the addition of these transformers, giving the AI some ability to direct their attention as to which of the weights to improve based upon the learning that they're currently doing. And I guess a pessimistic scenario would be this continues to scale for some time, another decade, let's say. And then it's like right now, the top AI companies are only working with the top universities. And 90% of the funding in this article is going to that these academics are getting is coming from these AI companies. So like a pessimistic scenario is this becomes this kind of top-down control. AI becomes this top-down controlled, highly, huge resources, highly centralized force for another decade or more, And then another scenario is we figure out some ways to democratize it. We figure out ways, better models for making these smaller systems, and everybody gets to play. More and more people get to play. There's more and more human machine teaming in the process of training, uh, and the systems become more, what I would argue is symbiotic with us, with the average person, not just this behemoth that they're throwing all these resources at, that has all these implications in terms of the future of our democracy and the way AI spreads. So I'd love to know what you guys both think about those two scenarios, or any others that we haven't discussed.
Now, you guys are probably an order of magnitude above me here, so with my crude understanding, but what I think Danko is saying here, John, is and that's why I really like it so much, is because what he's saying is that the system is not efficient. It's got this huge power law, which means that to gain more marginal benefit, you have to put so much more expenditure in terms of time, resources,
Yeah.
hardware, software, people, money, you name it, right? And that's
Yeah.
shameful and wasteful. And
Yeah.
while it's giving us some benefit on the margin, it only requires this kind of gargantuan productions behind it to make it actually happen. And
Mm-hmm.
so he's pointing at, and he's not only criticizing it, so he's
Mm-hmm.
not just hand waving, but he's also providing a suggestion for a solution which
Yeah.
could hopefully create an efficiency based not so much on resources, but about learning how to learn.
Mm-hmm.
And so and that's what intelligence, to a normal guy like me, that's what intelligence looks like. As
Mm-hmm.
Danko said, you take the average German off the street and he can do more impressive stuff than those systems which are hundreds of millions of dollars, and you need government involvement or Google and the big companies to make
Yeah.
it happen, right?
Right.
That's what intelligence is all about. Efficiency, in a way, right? Low resource usage, big computational output, right? That's what the
Yeah.
brain is. What is it, 40 watts or something like that?
Exactly. Yeah.
Right? So that's what makes us special. That's what makes us unique. So in a way, that's what I love about his point in saying that, and that's kind of, forgive me, Danko, but that's kind of also what Noam Chomsky said so many years ago. He said, to me, when Kasparov lost the game of chess, Chomsky said to me, that's like a bulldozer winning the Olympics in weightlifting. It's not so impressive. And I think he had the same structure or the same kind of context in mind, because the whole point is to do more with less. That's what intelligence should be all about, and with less
Mm-hmm.
knowledge, because we can't have the perfect knowledge, we can't have the perfect data, we can't have all the resources we need to build a house or to survive. We have to make do and improvise with scant percentage of what we would hope to have in an ideal world. And so right
Mm-hmm.
now, the way I understand it is, your criticism is saying, look, these people are always pointing us towards the ideal world. Throw $1 billion, throw 5,000 people, throw an institute behind it, throw government grants and support, throw 5 years, and then we have results. Fine, great, that's impressive, but that's exhibiting power law. And what we need instead, and that's the way, going back to your point, John, to democratize it, is like, break the power law, make it efficient, create a new organizational structure or process which gives us more with less of everything. And
Mm-hmm.
that's what the real breakthrough would be. And I personally love that. But let me ask you this, guys, as again, as kind of like an ignorant question maybe, but is this that we're talking about so far only at the software level? And should we not also consider the hardware level to improvise or implement your suggestions? Because the reality is, and I don't know, but the reality is we're using sort of a Turing architecture, von Neumann Turing machines since World War II. And is that a problem? Can we use those machines and make or implement your suggestions as a software sort of level on top of that hardware? Or do we need sort of a non-classic, non-von Neumann new hardware architecture that takes into consideration the neuro and biomimicry that you're talking about at the hardware level rather than the software level. Danko, what do you think?
I think it's fine to use John Neumann architecture. It's maybe not the most optimal way. Right? John von Neumann architecture is optimal for certain type of tasks, like most optimal for addition of numbers and things like that. But it does the job. It does the job with some inefficiencies. We could possibly build even more efficient architecture, but it's not critical. It's not central, right? It does the job. It's general enough. It's fast enough for such things. The computers can do a gigahertz or 4 gigahertz frequency. They can do billion times a second things that neurons in the brain are much slower. So yeah, it does the job. It could do the job. If that's all we have right now, it's not a big limitation. In the future, we may do it more optimally and reorganize it a little bit. But there are more important things to solve than that.
Okay, I get that. But again, the ignorant person would say, if we're talking about biomimicry and neuromimicry, and we're talking about 60 years of AI development, when, in the 50s, people thought it would be a solved problem by the end of the decade, probably one issue may have been, and that's obviously a sort of a marginal or minority argument, could be that the fact that the hardware never evolved, never changed, never moved on from the original von Neumann design. What do you think, John? Does that make any sense?
It makes a bit of a sense. It's a reasonable question, but I think this question of how general purpose is software on a von Neumann machine, how much of a universal Turing computer, how much can you explore computational phase space if you have a lot of von Neumann power, and we have a lot of compute power now. So I think the hardware, I'm with Danko in that the hardware benefits are going to be an optimization. They're going to be a speed up of what you can do in natural software. At least that's how they've been so far. We've created all these application-specific integrated circuits, ASICs, to speed up something that we did first in software. And that's been the general trend of development of hardware. So we usually find it first in software, and then we try and optimize it, in the process. The entire microprocessor is a copy of processes that were done manually by hand. So we slowly move our way, through these, like all the Boolean logic and stuff. We've moved our way into this model that's general enough we can do a lot of exploration. And if this autopoietic model is right, we should, at a certain point, start to discover that within the software itself, we can an Evo-Devo approach is just going to start beating out all the others at, for example, creating artificial life in these simulated worlds, at solving, say, improving, say, protein folding, right? And our understanding of that process. At a certain point, those things will happen. I want to plug a report that all of our listeners should know about. It's called The State of AI. State of, and then .ai. Nathan Benioff, who's an investor he's a venture capitalist at Air Street Capital. 4 years now, they've published this report. It's it comes out as a PowerPoint slide. It's about almost 200 slides. And they cover the research in the field, they cover investments, they cover talent wars, and they cover politics. They cover the whole space of AI. It's a beautiful report, and you can just click your way through and see what's going on in that space. And one of the really interesting things is that these models we just described, people are throwing them at drug discovery. So there's two companies, Recursion and Exscientia, who both launched as IPOs last year. And as you know, Nicola, I think we should all be invested in the market, not only in the top 9 tech titans, but we should have at least 50 different stocks that we pick that we think could be winners and put a little bit of money in each of them. And just like a venture capitalist, we can all be venture capitalists in this space. But if you had gotten into either of those two AI-backed drug discovery companies, Recursion or Exscientia, which both launched last year, they're both down about 70%. They're about down twice the market this year. And I don't think their models are yet tractable for what they want. They're not good enough. But what is happening in this space? One amazing thing slide that I got, or insight I got from that State of AI report from last year, 2021, State of AI, is they're using protein language models. They start with something like GTP, and then they take this GTP train, this physical language model, and they apply it to protein language, to protein folding. And this thing has created artificial proteins, and it's discovered that a set of new proteins in the lysozyme family for bacterial degradation of lysozymes that have only 44% of the same sequence as a natural protein, but they still work. And when they look at them, they did X-ray crystallography on them, and they discovered that all the same active sites are still there. The rest of the protein looks different, but the active sites, the pockets where the enzymes work, are still there. So from an evo-devo perspective, what do I see? I see, okay, you have to keep that developmental conservation of the active sites, but look at all the evolutionary change that this system discovered that's possible that still doesn't break the protein, right? So I have evo-devo on the brain. I apologize for that. But I basically think that they're going to be forced into seeing that there are these two fundamental ways that we can make progress with these, and we have to figure out how to put those two kinds of searches into our software and then later our hardware. Is the way that I would put it. And prediction versus exploration, back to the two boxes that we were talking about, that's actually built into a lot of the current AI models, that fight between a process of exploration and a process of prediction, that evolutionary and developmental. Development has to predict, reliably that cycle, right? So anyway, sorry for going on so long, but that's a really good question.
Okay, Danko. So John here has laid out what I think is a very good argument about his what he calls as natural intelligence hypothesis, meaning that in his view, the fastest way to AI is via biomimicry. And you have put your argument forward that the missing piece is practopoiesis, and it could give us so many insight and actually practically guide us towards the creation of that AI, so that we are a lot more efficient and we can do more with less. Now the question is, here you are, guys. Are you like two voices in the desert? As I said in the beginning, two people kind of that are like in the minority? Or is there anyone engaging, listening? Is there something happening with those two theses and the Practopoiesis theory of yours, Danko, and John's thesis? So is there any development or application or hope that these will be picked up and start getting implemented at a larger and larger scale? What do you think, Danko?
Yeah, okay. So first I have to share the fact that since I introduced Practopoiesis, the adoption from the world was much lower than what I was hoping for. That's a fact. And probably the reason was that the whole thing was too complex, too difficult to understand, too much work to think on, to sweat through, and there were shorter ways to get rewards, shorter ways to get achievements. And this is the case both in AI and in brain science, the same thing. And nevertheless, in the same time, there is like a small group of people who mostly don't know each other. I know, some who got inspired by these ideas and said, okay, that's where we should be working. This is where we should be going. And they did their little things that they could. So it looks to me that this is going to be a slow process. It's not going to be easy to make a change, to push it for different reasons. That some are intellectual, mental, difficult to change way of thinking. But even if you did change the way of thinking, then it's difficult to figure this out, how to go to the next step, how to create an AI out of that. I myself working on a company on a product that does like a small thing from Practopoiesis theory and applies it to deep learning. And I'm building it with two friends, a company. And we're now working on this thing for 5-6 years, slowly because we have other jobs, but we are working for 5-6 years, and it's only now getting to some conclusive results. Only now, after all this time, we had to figure out so many
Can you
things, so
share
many
any more
unknowns.
details with us about that company and the product that you're referring to, or the progress you've made, if possible?
Well, the company is called Robots Go Mental.
Love it.
It's basically technology that can do. It's called guided transfer learning. Right? So transfer learning is standard method in machine learning where you pre-learn the deep network with some related materials, and you basically your solution in this multi-trillion parameter space is closer to where you want to do because you train it with some other data that are related to that, and now you finish the training with the stuff that you really want to do. Right? That's the classical transfer learning. Now, what we were able to do is use Practopoiesis theory conceptually to develop a way for the network now to also to have guidance through this multi-trillion dimensional space, although we don't have enough computers to work in such spaces. We work in much smaller spaces, but the logic is the same. So learns how to go to this space. So it has some sort of intelligence, which dimensions of the space are relevant, which dimensions of the space are less relevant, depending on the inputs. So it also uses this pre-training data set, which is much bigger and richer to learn these new things. And then it has learned to learn, kind of. It's not full-blown thing. It's just deep learning improved a little bit. And it can learn much quicker, right? So it could learn from, in some cases, we could learn from one shot. In some cases, you could just use this learning instead of transfer learning, and it has the same effect as transfer learning. Just goes from far away from random set, and really quickly learns things.
It could learn from a sample of one?
In some cases, it can learn from a sample of one.
Wow.
Yes, in some cases. Not generally, just in some cases, like very special. So it has quite some advantages. Right? And now we are working on having it remember situations. So from the big data set, you have lots of, let's say a GPT-3 has to memorize everything about all the text, has to have everything stored. Like the whole entire mankind, what the mankind has written in the text, GPT-3 has it stored and collapsed everything. And that's why it has to be so big. Now, imagine you have a much smaller network that has seen all of this, but it kind of doesn't remember all of that. It's just a structure such that it can quickly remember it, quickly recall it. And that's something what our brain does with this. You remember this third box that I was talking about? What the third box does is it restructures the network that it had once had before. It kind of recalls the memory. When we remember stuff, that's what we do. We recall the memories. We don't have them.
We recreate them. Exactly. Do you have a name for that box? Do you have a name for that box?
Yes, I have a fancy Greek name called Autopoiesis. Right? Ana means over again. Right? So recreation.
Yeah, that's beautiful, because that's exactly what memory is. It's a recreation. That's why eyewitness testimony is so carefully. It's so easy to mess it up with the priming, the cognitive priming prior to asking the question. Yes.
Absolutely.
Autopoiesis.
I
That's
see.
beautiful.
Autopoiesis. Right? So we have created the algorithm for autopoiesis within deep learning, and it works to a degree. It's not perfect how the brain works, but it's the idea was let's change the least possible thing that we could add to deep learning technology that we have today, so that we would have we would get done as quickly as possible. Still 5 years of sweat, right? So it's how hard it is, right? And now don't imagine like building like real thing, like simulating all this like real brain and stuff with all these proteins with tongue twisting names that we were mentioning before, right? It's much harder. It's much more work.
What about you, John? You, John, discovered, if, and I'm not waving my own flag here, but you kind of discovered Danko's work during our previous interview together.
Yes.
And hopefully today, after we publish this one, we would have even more waves and kind of educate and spread that meme among the public and the culture and so on. But do you see any other signs that things are kind of changing or pointing towards the direction that both you and Danko want us to take us towards?
I do, and that's kind of a soft segue into this topic. I don't know when we want to get to AI alignment, but this field, because these things are so complicated now, and they're starting to handle so many important human decisions, there's over almost $2 billion now has been spent on AI alignment startups, nonprofits, public benefit corporations like OpenAI. Um, and there's this question of how are we going to make these things not just smart, but safe and wise. The really interesting question from my perspective is not just safety, because that's copying the immune system the way I would describe it. That's one of the big insights. But how do you make them wise? How do you get ethics? How do you get social ethics? And then within ethics, there's two kinds of values. So the subtitle of this book, which I recommend in my series, Brian Christian, this is his third book on the field of the future of AI. So he's finally getting it really, really well explained. Algorithms we live by, and I forget his other one, but this is called The Alignment Problem, Machine Learning and Human Values. And so it's the human values part of this book that I really recommend everyone to read this to get a sense of all the players in the alignment space. There's really only about 100 full-time paid people working in this space right now. It's really tiny. And yet, I think that a lot of them are struggling exactly with the questions you're asking. How do we control these things? What is our overarching model going to be? And here's the question that I got that found was the deepest in this. There's two kinds of values you can learn. There's the values of your trainers, and then there's the values that are universally adaptive. So there's human values, and then there's what we might call cross-cultural or universal values. So I would say that evolutionarily, there's a huge difference in our cultures of humans on the planet and in tribes, various tribes. But at the same time, where social psychologists are starting to understand there are certain fundamental values. We all talk about the golden rule and all the various meta golden rules of reciprocity and all the ethics that are encoded in our bodies. Now, some of those we know we have cognitive biases, and we know we have ethical. We know that we have too much negativity bias. We can easily have our amygdalas hijacked by negative things. So yes, there's biases, but we're a learning system, as Danko said, so we can learn our way out. And my question would be, do you guys think that we're going to not only have to figure out how to get machines to reliably learn the values of their trainers, but to reliably learn sets of values that we aren't even smart enough to describe what the right values are, but the machine will discover more of them themselves and self-stabilize? Because that's what I think a living network does, right? That's under selection. It self-stabilizes, and to me, that's where we have to get to. I don't know if that relates to your original question, but that's where we have to get to, I think, to get to systems that are beyond our capacity to directly understand, that are living with us.
Well, John, to take a moment here, that's kind of been sort of at the crux of, in a way, of what I've been trying to do for the last 15 years, is to bring the value conversation within technology, to bring in ethics, and to go a little deeper on how we do it. To me personally, and again, not as a cognitive scientist, not even as a foresight, specialist like you are, but just as a kind of simple ancient Greek philosophy background person, the key to education is not to tell the young people, or the machines in this case, what to think, but to teach them how to think.
Hmm.
To me, the key is therefore not to instill your values into the younger generation, but to give them a process within which they arrive at their own values. The key therefore is not to give them answers, that humongous database, that Danko is talking about and kind of poo-pooing, or making fun of a little bit, well deservedly in my opinion, but to point them towards how they can ask the best questions, in the quest of which they can arrive to their own answers. And this is how we make progress from one generation or another, I think, right? Because if we instill in our kids exactly the same values we have and everything, we just give them the answers and make them to just like recite them over and over again. Like, I'm sorry, but to me, like, the image I get in my mind is now how people try to learn some sacred texts by heart without any understanding or comprehension or whatsoever, but just like parroting in return. To me, that's the worst case of brainwashing, and exactly the opposite of what good education should be about. The good education is about the questions, not so much about the answers. So I think hopefully that kind of gives the box within which I think the AI values can be arrived at independently. Now, that process carries certain kinds of risks. There is no doubt about that, right? The control problem is here very clear, because and that problem, the control problem, exists for our children. I mean, you can have children, you can give them the best of education, the best of upbringing and everything. Ultimately, they would be the ones to make their own choices and decisions in life, and you cannot control whether they don't turn into the next Putin or the next, Hitler or what have you. You can do the best to kind of direct them in the right direction and therefore improve the probability, but you can never preclude the possibility that they may turn out otherwise. And I think that is in keeping with good education, also personal freedom, and recognizing the fact that ultimately, at the end of the day, our children, and of course machines will be our future children, as Hans Moravec said, is to recognize their independence, their autonomy, intellectual autonomy, and the fact that you can do only so much, and at certain point they will be on their own, just like our children are in the world. And so there is never a guarantee of that their outcome would be our best case desired outcome. But going back, that's kind of like my take on it all. But going back, John, to you again, perhaps maybe this is, unless Danko, do you want to add anything to this before we move into the alignment issue?
Please move. Please go on.
Yeah. Okay. So John, I think this is perhaps the best time for us, following your good, foresightful, insightful guidance, to talk about the AI alignment problem. So can you please define it for us, because some of our listeners may not be familiar with it, and give us kind of the implications of what biomimicry and neuromimicry can help us with in accomplishing this kind of so-called AI alignment?
Okay, well, first, yeah, thank you for bringing values in, and your Socratic question-driven approach. I Nothing would excite me more than to have these deep learners that everyone's working with get smart enough to start asking us questions that actually are beneficial to our answers are beneficial to it and to the interaction that we have with them. I think there's an entire industry now of prompt engineering, right? Where people are actually studying how we ask questions of the Google brain, which is one of the most complex versions of these instantiations right now, and trying to respond in a more useful way to us. So I would think that, optimistically, I would think that that's the very start of this Socratic future that we want, where we're training the AIs to be good learners. But here's how I break down the problem of control. So as I was saying earlier, there are these two obvious kinds of control. Can the system do, well, there's three. Is the system doing what we tell it to do? That's the basic control problem. Or is it deviating from it? Then we bring in values and say, is it respecting the values and the guidelines that we gave it generally as guiding principles, that it applies in new situations where we didn't specify what we wanted it to do? That's a second alignment problem. And then the third, that I consider the most interesting, when we're not smart enough to specify what the value should be, but we've given it what we think is the most cognitively diverse, useful set of values, is it going to come back to us with questions or evidence, thoughts on really what would be even a better set of values than what we're using? Those would be those universal values that I think we're all skating towards. And I have to qualify this, only on a developmental side of things do I think those exist. On the evolutionary side, we're constantly creating new variety, and we can't predict what's going to be good or useful. Only selection is going to do that. So for me, I break down alignment from this Evo-Devo frame. I said networks sit at the top as an interaction between evolutionary and developmental systems, right? So for me, the alignment problem breaks down into the intelligence, which I consider a fundamental evolutionary driver. Intelligence is very dangerous and exploratory and creative, and there's many kinds of it on the planet and in our own brains. Then there's security. So security, that every complex system has an immune system in it that keeps it working, and a set of developmental genes that keep it on its cycle. So is intelligence and security. And then the interaction of those two, for me, is ethics and network ethics. It's how systems that are trying to protect themselves or be secure, trying to create or be intelligent and figure out new ways to create, how those two, creation and protection, work together to adapt. And so for me, the ethics or values, the rules that individuals and groups have to use to work together, those are critical. And so life has a set of natural ethics, natural security, and natural intelligence. And in my posts, I mention people. There's a person, Rafe Sagarin, an evolutionary or a marine biologist in Monterey, who recently passed away. He started a Center for Natural Security. How do we learn from nature to create more defensible computers, organizations, and societies, right? And he published this book, Learning from the Octopus, which is all about these lessons we can learn from nature to create more natural security. So I would break alignment into these three questions: safety or natural security, smartness or natural intelligence, and wisdom or natural ethics. And so to me, and I put the wisdom at the top, right? A network always wins, right? A well-built network, even if individuals and groups don't, they're being selected in or selected out. But the network of life as a whole has been winning for 3.5 billion years. So that's why I would put a natural ethics or natural wisdom or whatever you want to call that, natural values, at the top, just like you would, Danko. And so that's my overview. And then just come back to this book. I want to plug it again. It's a beautiful book. It's only like 300 pages.
I should
you
really have him on the podcast.
you should. He's wonderful, and he's a visiting scholar at University of California, Berkeley right now. Very nice guy. I followed his Twitter feed. So the alignment problem, it's a big problem, and I'm breaking it down using my Evo Devo frame into those three things. I'm sure there's other ways we could break it down. It's a huge problem, and there's now people and institutions working on it. And I'm hopeful as the machines get more powerful, they will move more towards these neuromimicry and biomimicry approaches, and they'll start to understand the real importance of these model-based approaches that Danko's take, or theory-based approaches that Danko's taking, where you try and figure out the basic theory that living systems use well, and then how do we apply that in these still very brute force models that we're using in AI.
Okay, let's take that ball and pass it to Danko and see if he can play with it within the realm of his Practopoiesis theory. So Danko, presuming that you accept this kind of slicing of the pie into security, intelligence, and values. Was it values, the last one, John?
Mm-hmm. Ethics, that's what I call it.
Ethics or values, yeah.
Yep.
What can, if anything, Practopoiesis help us with in any of those three realms?
Yeah, very interesting question. So I have to first admit that I don't spend personally a lot of time worrying about ethics and security. And not for the reason that I think it's not important. It's very important. It's essentially important. But I'm just one person, and I kind of decide to put the time and hours I have into something else. I'm glad, really glad that other people are worrying about stuff that I don't choose to worry about. Even more important than what I do.
Well said.
But as listening to John and making notes and reading his podcast or reading his blog, listening to podcasts, I have a few insights here. One is that intelligence on these levels that we described, each level has knowledge, certain knowledge, and it acts. So Practo acts and creates something. So the security and ethics has to be stored somewhere along this hierarchy, somewhere in this knowledge, has to be there. Right? And in a way, you cannot directly distinguish intelligence from ethics, because acting ethically is also acting with knowing what the right thing to do is to achieve certain goals. Right? It's more abstracted. It's a more general way. It's different type of goals. It's not maybe a personal goal, but a goal. You're achieving the goal of a society, goal of a group. But it's still a goal, and it's still intelligent thing to do, to have a knowledge that you should act in this way. So it's somehow all intermingled. You don't lose a possibility to develop ethics by developing a smart machine. And yet, of course, you have to be very careful to do it right, not to ignore this problem and to let machines go astray and do crazy stuff that don't fit our ethics. Right? So since my work is to figure out how the machines learn, my hope is that once, if I can give to John look, here is a good way how machines learn. This is how you can manipulate them, make them learn what you want. Now, John, since you're working on ethics, you figure out how you are going to use these rules to or you don't even have to figure out. You just go and use the rules and build in the ethics that you have found out to be relevant and needed to be in the machine. So I think that's how how the division of labor should be. But having said that, there's one more thing I did think about, and that's like, I asked myself, where are we humans at worst? What is it that we need to like not make sure that machines don't get exposed to, the connections they shouldn't have, the knowledge they shouldn't have, that makes us worse? Where are we at worst? And by looking at human behavior and then explanations of human behavior, it becomes pretty clear that there's one fundamental thing that makes us do the evil stuff, and that's fear. We have fear, and fear is somehow behind lots of evil things that you do. Like the narcissistic personality disorder comes out of fear, out of having difficulties as a child handling fear. And you are basically, through a narcissistic disorder, you're into all the unpleasant things these people do, come out of their own fears that they couldn't resolve, right? And things like that. So fear is somehow fundamental. Also, like a tyrant that has a big country and wants to have a bigger country. We are not going to name anybody. It's a fear. Somehow, fundamentally, it's a fear. It's not enough. It's never enough. I'm still scared. I'm still scared, and I need more power, more something, more this, more money, more this. And then and people go and do evil stuff. Now, so machines should not have fear. That's my conclusion. We should be very careful on whether we give fear to machines or not, because fear has this. Fear comes from the need that our biological body needs to pump up the energy to act, like flight and fight response, and so you have to like push up the energy into the organism. But still, that's not yet fear. It's this energy plus interpretation. And interpretation could be very positive, like I'm having fun, I'm enjoying, I'm having the best time of my life. Or it could be like the worst time of your life, because you have this energy and you don't know how to use it. You cannot use this energy. You cannot channel it out. You have to kind of try to push it down there, because the world puts you in this situation. That's when you say, I have fear. I'm afraid. And then not controlling this properly, you go astray.
Let me grab this, Danko, because I think this may be one part that you and John need to work out, perhaps. And the reason I'm saying this is that, and John, you correct me, but I'm going to hand off this ball to you here. You're talking in one of, I think it was part 3, perhaps, of your Substack series, where you're talking about emotional AI and how, quote, emotions are a primitive kind of consciousness, a metacognition. So fear is a kind of emotion. You're saying that we need to have emotional AI. So can you have emotional AI without fear? And first of all, and secondly, why should any AI have any emotions whatsoever anyway?
Yeah, well, let me take the emotional one first and then the fear one second. So I think emotions are this brilliant state summary that brains use when they have logical log jams and disagreements amongst each other. I quote Damasio or Descartes' Error by Antonio Damasio, the neuroscientist. That was I think came out in 2003 or something. It's a classic in neuroscience popular literature, because it was one of the first that described these people that have lesions in their amygdala, one area of their limbic brain, emotional processing, and they don't have access to their own gut feelings. They don't have conscious access, at least. They might have unconscious access, but they don't know, when the hair stands up on your neck sometimes and you can feel it and you can describe it. They can't do that. And these people will endlessly argue the logical positives and negatives of a decision, but they don't make a decision, and they can't tell you which one's better. If you have access to your gut, you can not only get a gut feeling which one is better, but your gut pushes you, motivates you to actually make a decision based on your selection. So there's this kind of emotional, I think of it like a primitive consciousness. It's a kind of a state summary of the states of all the arguing neural networks that are making their rational, classifications, and then it works beautifully with that process and pushes you to do something. So I do believe we need something like that um, in these AIs, because they're going to be computationally incomplete just like us. They're going to immediately be overwhelmed by the power law uh, capabilities that of combinatorial complexity that Danko is talking about, and they need some way to guide themselves in a world where they're going to be not godlike in any way. They're just going to be, in my argument, just more complex versions of us. As to the fear, I would agree with Danko if we're talking about what Daniel Goleman, the emotional intelligence author, calls amygdala hijacking. He coined that term, where your amygdala gets you just floods your brain, right? It shuts down those systems. It over focuses its attention on some triggers, and then boom, right? And then the system just doesn't work, and you get these crazy things that are counter to a person's self plan and to their model of what a good world is. If we step it back though to pleasure and pain, we find analogs to pleasure and pain in the simplest cells. Now we wouldn't call it pleasure and pain, but we do. Gabor Mate, the great addiction psychologist, he talks about how we have these feelings of I want to bring something closer to me or push it away from me. Well, there's these beautiful gene protein regulatory networks, even in a simple bacterium, that will take copper that comes inside of the cell, and immediately bind it to the cell wall because it knows it's going to interfere with its DNA replication machinery. And it knows also, when it's looking at gradients of food, which to move toward and what toxins to move away from. So I would argue that pleasure and pain, or attraction avoidance, they're these kind of things that we scale up towards. And at a certain point, they're going to need that kind of emotional nuance. And maybe they won't need fear if we're defining it as a flooding process, but they will need some gut model of, oh, that's not right. I don't want that future, and I don't want to do that thing you told me to do because that's not ethically right. I want a car in the future that will creatively, even beyond its programming, defend itself against being weaponized, right? That's one of the examples I give in the that to me would be a serious level of alignment in a system that is deeply natural and much more complex than us, and fast in certain ways. So I don't know if that resonates with you, Danko, in terms of the way you look at emotions, but no, that's how I would take it.
Well, I have to admit, I don't have a good answer in this case. I don't have a good answer because, as I said, it's not really something that I spend lots of time thinking about. And these are all interesting things. I have more questions than answers this time.
Well, that's what we're here. We're here. The great question asker is right here.
Well, let me throw in one more question then, because that kind of comes to mind right now. Since we brought in, emotional intelligence, since we brought in values, since we brought in security, and that's to both of you. Let's start with John first, perhaps. So let's say we do follow your advice, guys, and we do create AIs, or we start working on creating AIs following the guiding principles that you are outlining here. Does that mean that we have better chance that those AIs would be more ethical, that they would be emotional like us, and that they would be safer? In other words, is the benefit going to come out to pay off in sort of like enhanced safety, enhanced values and ethics, and enhanced I don't know what would be the upshot of the emotional, but maybe action, as you said, because you were giving the example, Demasius, that people are kind of locked in this ever kind of analysis paralysis, who lack the emotions. They're constantly analyzing all the possibilities and are unable to take any action.
I would say it's more wisdom. It's both a wisdom of knowing when not to do things, but it's also the action. But it's the more fundamental thing. If emotion really is a kind of meta cognition, it's kind of a wisdom when you can't even rationally describe what the next action should be. You have a gut that's guiding you to doing or not doing certain things.
You know what this reminds me, and I'll give you a chance to answer my question, but what this exactly what you just said reminds me is I just interviewed Professor David Loy, who works on who is a professor of Western philosophy and a Zen Buddhist teacher. And he works on the connection between modernism and Buddhism, because he talks about the fact that, probably the greatest accomplishment in the West, historically speaking, has been our social progress and revolution. But in the East, it's been sort of personal enlightenment and insight. But the reality is we need both to survive in the 21st century. And so he was telling me this kind of Zen story, as they tend to do, about a student asking his teacher, his Zen teacher, okay, teacher, what is the fruit of a lifetime spent in meditation and Zen practice? And the teacher said, appropriate response. Right? And I think that goes at the very essence of wisdom, right? And exactly to what you, John, were just saying about knowing when to act, knowing when not to act, and knowing how to act. That's like the essence. The appropriate response is like the essence of it, I think, really. So, but anyway, let's go back perhaps now to the original question.
Yeah. Well, I like to bring Aristotle in, in his good, true, and the beautiful. And Aristotle way better than I ever will. But as I understand it, the good is the most important for Aristotle, and then the true and the beautiful are contributors. They're important values. But the good is really what we should be meditating upon as much as possible, consciously and unconsciously. And if we're doing that individually and as a society, then that's a fantastic place to be. But how do we get to that? I think we get to that only by creating more beautiful and searching for more truth. So those are the beautiful is evolution. Evolution is just incredibly beautiful and various, and some things are better adapted and worse adapted, but it's constantly creating new creative beauty. And then the true is this subset of developmental and big picture things that we've sussed out about the world, that they're the bedrocks, the science and the protection we build around the things we can predict. And I think we have to pursue both of those in order to get to a nuanced model of the good, how we balance exploration and creation and protection. How do we balance those two to be adaptive? And maybe it's only the environment that selects the ones. Maybe we never but I think we can get better models of how to be that way. We can get better models of the good. So I would see a future where there's lots of little personal AIs. We're all using AIs and training them, and there's incredible diversity, and some of those are being used by bad actors. But we have very strong, like, security systems, immune systems. Remember the spiders in Minority Report? Federations of all these different actors. No one world government, but just like networks, multiple networks protecting us. And then we use swarms of the ones that are loyal, that we've trained as trusted, to overwhelm the rogues on the network edge, just like humans do. We find the ones on the network edge, and we do need them. Evolution shows that occasionally the rule breakers steer us to the next level, right? So you have the geniuses and the sociopaths, on these two outside edges of this normal distribution. But as long as most of the things in the middle are good, I think that, to me, is the best kind of security we can expect. is a future will be messy with lots of diversity, but then the majority will be trustable and, wise. The majority will be adapted.
Danko, let me pass the ball here to you. And with this kind of qualification, I was kind of setting you guys up here a little bit because uh, there's a lot of people who think that the fact that we lack biomimicry and neuromimicry may be a benefit rather than a cost. Because one of the lines of reasoning here goes along the idea that, look, we are the most terrible beings on our planet. We are talking about values here and security, but the reality is, as Yuval Noah Harari says, Homo sapiens is a mass murdering species. Every time, everywhere we show up, species start going extinct one after another. Then, if you look at how well we deal with our value or the security of not only other species, but even our own selfish security, we are supposedly failing at every single level. And of course, therefore, we are kind of failing in a way to live up to our own values or to those universal values that John was talking about, because someone would push it to the point and say, look, if we get into a nuclear war now with Putin and all of that, we're going to wipe out the network. That whole network would collapse, would disappear, would go extinct because of our own stupidity. So therefore, we lack the foresight to have enhanced security. Our values, we don't live up to them. And our emotions or our intelligence are failing us in the sense that we are kind of driving the train towards the train wreck. And so, therefore, we don't want AIs to be like us, but we want them to be not like us because we're not doing a good job. And many people are putting the hope that our only hope, therefore, is if they're unlike us. And now, John, you're telling me that we need to follow neuromimicry and biomimicry because, actually, contrast to what I've just outlined, they would be safer, they would have better values, and etc., etc. And how do we work that out? And aren't you, Danko, concerned that if we follow your Practopoiesis theory and if we apply it and we create those AIs, and if they're more like us than unlike us, they would end up doing even worse damage than what we've done so far? And would you not be responsible in a way then? And like,
Love your questions.
Okay. Yeah. Okay. Now, if I get responsible, I gotta think about it. So here's. I mean, I agree with everything you said. Like this question is really on a place and really great question, right? We have a tendency to talk about ourselves like we are like divine or God-given creatures, and then at the end we just selfishly destroy the planet or in species and all that thing, right? So what kind of values are our values?
we called ourselves Homo sapiens, the wise man, but I like to call myself what Douglas Adams used to call us, which is uh, an ape descendant bipedal life form. That's to me capturing it a lot better than the Homo
Yeah.
sapiens, because I'm a lot more of an ape than really a wise person. Let's be honest here.
Amen.
Okay. Uh, so let me tell you what I think about it. So we have developed all this advanced intelligence, but this came on top of all these drives, like survival drives that are reflected in our emotions. That and then the intelligence starts serving the drives, right? So we are not really asking, or most of the time, we are not asking questions how to save the planet, but how to get something for myself, how to survive. First, we started with survival, and then more and more collecting stuff, industry, civilization, all that come from selfishness, basically. And now, fundamentally, all that comes. Really crazy thing is that all that comes to our body, to the energy that we give to our body, because anything for our body to do, it needs to pump up the energy the right places, it has to distribute it right. And that's why we have different emotions, because emotions are basically putting our body in a prepared state to do certain type of job. If you have to fight someone, it's not the same as if you have to hunt an animal. It's
Or you play the
overlaps,
piano,
but
yeah.
it's not the same. Or play piano is much more different. Having producing kids next offspring, it's a completely different set of emotions that you have to go through to get a partner and all that working thing. Now then the kids start annoying you and you start educating them, a completely different set. So it's all all set up as a sort of a force and driver of this intelligence. Now if we build the intelligence without the driver or very weak driver, which we will have at least at the beginning, now what comes, I don't know really, but it's not really a replica of human. It's something that's intelligent but doesn't have all these drives. Now, why it doesn't have drives? Because we have robots that don't have the robots that we will build, at least the first versions of the robots that we build, will not have this problem of having to pump up energy because they can get energy easily. They have just battery and electromotors with enough watts. That's it. You just run the energy through, and that's all. You don't need that all this thing that we needed. We needed in order to run away from a lion. And that will affect quite a bit of a palette of emotions that the robot could have. Like it will restrict it because the whole thing is so simple.
Yes.
The energy part is so simple. Now, if we want to get creative, we could get creative, but we don't need to. There is no practical need, and probably we will have no choice but have a restricted emotions on robots. And it will probably be good because our emotions tend to make us are genetically selected for us to survive and not to care about the rest of the biosphere. Because back then it was, we were kind of on equal footing, competing with each other. But now we are so smart and still have these basic emotions that drive: grab, destroy, eat, take for yourself. And these two things are not good for us, and we shouldn't give them to robots. And we don't need to give them because they are just having, electromotors or whichever motors you want to have and batteries. So I think the answer is somewhere there. They're never going to have our palette of emotions.
But do you agree with that, John? Because if you have emotional AI, then while I like Danko's point that there will be a kind of a different spectrum of emotions than our human spectrum of emotions. That makes perfect sense to me. Does that mean that there would be no overlap? Because I would say maybe there will be some overlap between our emotions, and therefore they may be exhibiting or experiencing some or similar to many of our, maybe not the same, maybe a lot wider spectrum, but at least some of our emotional overlap there will be between us and the robots. And then even more so, one level above that, how is that going to make them safer, wiser, with higher values and all of that, if they're kind of like us, and yet you're thinking that they wouldn't make a worse mess than we have, according
That's
to some
right.
people.
Well, this gets back to Danko's original point about learning as kind of the second box. I may have a slightly different view of learning than him, or maybe I use a different word. But for me, there are these two kinds of learning. There's this the learning of the things that work for me in my context, this evolutionary learning. And then there's this developmental learning, a learning of a subset, small subset, the 5% of things that are going to be useful in any context. And that I want to protect that learning and build it as a core of my self-protection and my eventual advancement through evolutionary trial and error. Eventually, I feed back in the evolutionary learning to development. And in our genes, we have these accretive genetic systems. So, we just built on top of the nematode, right? We pretty much have that same subset of in the developmental genetic toolkit of cycling things that they learned, and then we added all these other features to manage those hierarchies that we see in Practopoiesis, these hierarchical layers that sit on top of the other layers, right? So I would argue that you're going to have emotions every time you run into a logical incompleteness. You need some state summary of the whole system, some network summary that guides you. I think Danko's right. It's a different substrate, so it will be a small subset of our palette, of our current palette. But I could still imagine a use for jealousy, for example. I can still specific examples. Now, it would be regulated far better. You know, it wouldn't be this kind of rage envy that we get. You know, um, like when you feed a rhesus monkey a grape for a task, and the one right next to him gets has only been getting cucumbers. That one will immediately throw up his arms and say, "I'm not playing your game anymore," right? And that's like a serious like comparative envy thing, right? That turns into this rage. So and recruits all those energy things that he was talking about. So I think it'll be some far more nuanced version of that. But I also feel that there'll probably be a new set of emotions, because it's a different substrate, a new set of fine-grained emotional understandings of both the evolutionary and developmental side of things. I like to think about a fly. People say, "Oh, the AI that's coming is going to be a singularity." And I say, "Well, no. If it's an Evo-Devo system, there's going to be these developmental features, including these fundamentals of its emotional intelligence, if you will. It's still going to love its neighbors. It's still going to have some desire for the good, whatever we're going to figure out that is. But that fly doesn't understand me, and yet it does. In its genes, its nervous system is so jacked up that it can actually see the light dark oscillations in a fluorescent bulb. That's how fast its brain is, right? And so it's looking at me trying to swat it, and my hand's coming down like this, like in slow motion, right? And it's this super jacked up system with a very simple brain, and yet developmentally, it totally understands me. It's got all my physics hardwired in. Only evolutionarily does it not understand me. It doesn't need to, because it's so much faster. It doesn't even need that. And I would argue that that's kind of the future that we can imagine, is there's going to be these AIs that will have this developmental understanding of the system, of how the universe works physically and informatically, right? And that's going to have to include an emotional gut when the brain doesn't work. And so I don't think it's a future most people want, as you mentioned. Who wants to give emotions to our robots? Doesn't that sound terrible? Now we're going to have to start treating them ethically. Who wants to do that? Who wants the complexity of having to build a new robot and argue over whether to turn it off or all that crap, right? Or whether it's feeling pain? I don't think we're going to be able to get around it. I think there will be will be required to have some of that. There'll be some discussion of, I want to minimize the unnecessary pain that this robot feels as it's being trained. It sounds science fiction-y, that future. I understand that, and I see why people would react to it. But I do feel that some analog to that has to be in these systems, because they seem to work so well at all levels of existing systems. I'm not saying flies have emotions, but but there's the integrated information theory says that bees have a basic level of consciousness. I buy
Yeah,
that argument, that there is this. So
continuum.
that's one of Danko's proposed top layer networks, right? Is the consciousness layer. So my argument is you got to have the basics of those in those systems, or they're just not going to scale. They will not get smarter. There'll be a certain point at which they'll stop, or if they scale, they're going to be dangerous.
Yeah, that's actually my last question here, guys. Before I bring it to a close here, because we're kind of over 2 hours now, and I wanted to throw it to you, Danko, because uh, if I'm correct here, we've arrived at consciousness. John is pushing us for emotional machines. You, in your new paper, which has some, again, it's called Where is the Mind Within the Brain? Transient Selection of Subnetworks by Metabotropic Receptors in G protein gated ion channels. People should Google it, it's fantastic. But if I get this right, in a way, you're kind of showing where consciousness may be located and kind of how it may work too. So, to both of you guys, but Danko can start us up perhaps as kind of like a towards our closing of our conversation. Does that lead us all towards consciousness and the fact that perhaps what we've been missing in the past and what we must gain in the future if we have to have artificial general intelligence is to have this consciousness, and that perhaps we can't do it without it?
Yes, I would say definitely so. If we want to have highly intelligent systems that can do this variety of different situations that have lots of zeros that you, Nicola, said is infinite, you have to have consciousness. Consciousness is not something that you have in addition to intelligence. Consciousness is, so to say, price to pay for the intelligence. Or we are consciousness through these internal computations, resolving things to figure out what the next right thing in this situation should be, and we do it. We, as a result, we experience all the conscious experiences, and we act as if we are conscious. So yes, definitely the robots will have to be conscious and very, very conscious. Maybe not as emotional as we have discussed. They will be conscious about other things rather than their own emotions. They may not ever, come up with what you just said, jealousy. Maybe they could, may not. They may never come to their mind of jealousy, but they will be conscious about other things. And to be intelligent, you have to be conscious.
John?
Nothing to add. That sounds. I totally agree with everything you said, and yeah, it's going to be a really fascinating thing when we start getting to robots that, as Kurzweil said, eventually the AIs are going to claim to be conscious, and we will be exponentially persuaded by them. Like, we won't agree at first because obviously they have to. We can't know. Maybe we'll get a theory where we can measure it eventually, but still we can't really know their subjective experience. We have to be convinced by it. I think the same is going to happen with emotion. There will, and I think that might happen earlier, right? There'll be this earlier sense of this thing. You can almost say that it's happening now with these dopaminergic reinforcement learners, where if you squint hard enough, you can see in some of these trainings a system that seems to get it's called learned helplessness. It's amazing. You know how a dog will learn, every time I leave the cage, I get shocked, so I'll just sit. This was Martin Seligman's term, the positive psychologist. Eventually, humans get it too. After a certain period, they stop working. Well, these AIs, after a certain amount of exploration, if their prediction is too strong in their exploration prediction balance, they'll just predict, oh, I can't do anything. I'm just going to sit down. I'm not going to explore the Montezuma's revenge anymore. I can't get out of the maze. And is that squinting very hard? That's a kind of depression, right? And is that as these things get more nuanced, will we just see more of that in them, and will it actually be truthfully biomimicry in that sense, and neuromimicry in that sense, not just something that we're projecting on them, but a real process? I would argue that that's the way we have to go. But as you guys know, I'm biased to that way of thinking, and maybe I'm optimistic too. I'm optimistic that the future of human machine convergence and the singularity is this kind of just another version of the same thing, but at a more complex level. That to me is a very nice way for the future to unfold, and so I should recognize that I might be biased there, and I really appreciate it when we try and poke holes in that.
We're all biased, but I think your biases, guys, are poetic and at least poiesis, but to me, poetic. So let me ask you before I give you the last word here for our kind of takeaway messages, Danko, what's the best place for people to find more about you and follow your work?
Don't forget his He has a Practopoiesis website, don't you, as well?
It's a part of Danko Nikolic
Yes,
website.
it's
So you will find it
very
there.
highly Google ranked page.
It's very
All right,
unique
that's
term,
good.
right? He coined the term, so of course it will be very highly rated. I
Yes.
hope deservedly so. And I would also add to people to Google that paper that I mentioned several times in your most recent book. And what about you, John? What's the best place for you?
Well, I think relative to this conversation, I would say the Substack, which is natural alignment dot Substack, um, is .com is the 7-part series on what would the future of AI look like if it has to become more neuromimicry and more biomimicry? How do we align these things if that's the way it has to go?
Yeah, I've been fascinatingly following those as they come one at a time. I think we're now about maybe 60% in, with probably four of them published out of seven or something like that.
Yes, sir. Yep.
So
Yep.
I would link to them for sure, and I highly recommend them. They're kind of long and demanding, but they're
Yes.
worthwhile. So I highly recommend them. So let's start then with.
Nicola, if I can just jump in, I forgot one website. It's called Sapien Labs. I have it's a neuroscience labs, and I wrote there some 20 or so blog posts about Practopoiesis and related topics. So people who are interested may look at their Sapien Labs.
Fantastic. I would link to it. That's a great addition. So, John, we've covered a very wide variety of topics as we usually tend to do, but in a way, we kind of managed to mostly stick to our main points of reference today, which was bio and neuromimicry as the allegedly best ways to create artificial general intelligence and some of the implications with respect to the AI alignment problem. How do you wrap this conversation up, John? In your view, what's the message you want to send us away with today?
Well, I would say the one message I feel very strongly about is that life is by far the most miraculous and amazing thing in the known universe. I used to think it was the brain, and then I realized no, it's this genetic network that produces the body and the brain. How is it possible? Because that includes the brain. How is it possible that this tiny seed we can't even see unfolds to create us and does it so robustly and reliably? Unbelievable. And then you look closer and you see of these 25,000 genes that we have, these control parameters, only a tiny subset of those are this critical set that manage the chaos. And so I think the big insight is that there's some deep lessons for us in understanding these natural autopoietic systems better and how they create these hierarchies and these modules that Danko's talking about. How they've done that not just in us but in other replicators. Um, people look at even the universe itself as an potentially autopoietic replicator, the cosmological natural selection hypothesis. So I think there's some deep insights from nature that we're going to get in building smarter, organizations and societies and technologies. And so that would be my wrap up. Is perhaps this model that I've mentioned is too precise, but there's something really, really special and amazing about life as an autopoietic system, that there's still a lot more for us to learn in creating safer technologies.
And what about you, Danko?
Well, I would say simply we need the third box. So we had so far the two boxes. One was plasticity or learning. The other one was the network that this learning has created. And that's how we built brain sciences around these concepts, and we built as well artificial intelligence around these concepts. And we need a third box that sits in between the two, and that's the one that is gonna give us full intelligence the way we would like to have it.
Well, guys, I, for my part, have to say that it's been a bit challenging, but emotionally and otherwise and intellectually extremely rewarding. So thank you very much for being with me today.
Thank you, sir.
Thank you, Nicola.
If you guys enjoy this show, you can help me make it better in a couple of ways. You can go and write a review on iTunes, or you can simply make a donation.